Hello everyone. Today we are going to start Unit 3, Energy. And in this video we're going to address three main ideas. Work, the science type. We're going to address potential and kinetic energy as well. So let's think back all the way to the beginning. The two variables that we first met were distance and time. Now, distance and time, these two variables are really good at telling us where we were and at what time we were there, but that wasn't good enough. Well, what if there's a change in distance over a time? And that gave us a velocity. And again, that wasn't good enough. So what if there's a change in velocity over time? Well, then velocity and time comes together and gives us acceleration. And then we brought in our friend mass, kind of like a strange traveler from a distant land. Mass comes in and gets together with acceleration, and we get a force from it. Now, these first few units that we're doing are all based on distance, time, and mass. So let's write F is equal to ma. It all starts here. We already have this m here, so let's choose one of these two. If we multiply this equation by t, that's going to bring us into the next unit. So right now, let's multiply this equation by d. I'm going to rearrange this just to write it in its proper form. In the last unit, we only considered the forces that are acting on something. We didn't really consider how supplying a force for a longer or shorter distance could affect the motion. So if we apply a force over a short distance as opposed to a longer distance, something about the car's motion will be different in the two cases. So the force in the shorter distance versus the same force just in a longer distance. Obviously the car went a little bit further. So we're going to be exploring this idea of work. This is an equation for your notes right here. Work is equal to force times distance. So applying a force over a certain distance will change something about that car's motion. So let's switch gears here for a second. We have that work is equal to force times distance, but work is also equal to mass times acceleration times distance. Let's switch gears here and let's think back to Unit 1, to one of our kinematic equations. And let's consider our equation that starts it all. Of course, F is equal to ma. So we have two equations here, and somehow we would like to combine them to make another equation for work. So here's a distance, here's a force. So let's see if we can rearrange some of these equations, put them into each other to come up for another equation for work. So let's start with this one up here. I'm going to rewrite it. And notice that in F equals ma we have an acceleration. So we can solve this equation for acceleration. So all I did here is I divided by 2 and I divided by d and brought it over to the other side. Okay? So now we have an expression for acceleration. Let's plug it into F is equal to ma. So we're going to take this and we're just going to plug it in right here. And then we're going to get something that looks like F is equal to m over 2d times v final squared minus v initial squared. Okay. And now we have a d on the bottom here, so if we multiply both sides by d, we can get our work equation on the other side here. So that d is going to cancel with that one. And what I'm going to do now is I'm going to take this and I'm going to distribute it into each of these terms. So we're going to get force times distance is equal to we have a 1/2 mv final squared minus a 1/2 mv initial squared. So now we have two equations. We have two equations for work. We have work is equal to 1/2 mv squared, and we have work is equal to mass times acceleration times distance. Well, you're probably thinking, well, how can this be? It's an equation. It should only equal one thing. Well, this is where this idea of energy being a shapeshifter comes in. They're kind of like Mystique from the X-Men, always shifting from one form to the next. This form of work and this form of work are in fact two sides of the same coin. These are just two different forms of energy. And if we're talking really specifically, right here, we're talking about the energy that's associated with something with a mass moving at a certain velocity. And what we're going to call this is kinetic energy. And I represent kinetic energy with a capital letter T. Let's revisit this guy over here. We're going to get force times distance is mass times acceleration times distance. Let's replace these variables. So we have force times distance is equal to, we're going to leave mass the same. Well, hey, we know an acceleration. That's g. So if we're going to apply a force against gravity, and we're going to replace d with a certain height, we get another equation called potential energy, and I'm going to represent potential energy with a u. Mass times gravity times height. So if I have a mass and I'm going against gravity and I'm lifting at a certain height, I'm going to give it potential energy. So let's see if we can formalize a definition for work. So over here we see that when we do work on something, whether it's lifting it up or giving it some sort of motion, it means that we're giving the system some energy. So when we do work on something, we are giving a system energy. If we briefly look at the units here, work is measured in joules, a unit called joules. Kinetic energy is measured in a unit called joules, and potential energy is measured in a unit called joules. The units have to be the same because when I do work on something, I'm giving a system some sort of energy, whether that's kinetic or potential. So the thing about work is that it only counts in the direction that the object is moving. Okay? Now, this is a really important concept, and it's something that we're going to explore more in class tomorrow. But for now, let's look at an example. Let's say it's the nice warm summertime, and you're given the task of mowing your lawn. And let's ignore friction for now. We'll get into friction later, but let's ignore it for now. And let's say you're going to apply a force down on this handle. Your force is going to be equal to 10 newtons. And let's say that you are going to push the lawnmower a distance. First it's here, you're going to push it a distance of 10 meters. So you're here pushing your lawnmower, and you're going to push it all the way 10 meters. So initially you might think that, well, this is a pretty simple problem. Work is force times distance, and 10 newtons times 10 meters is just 100 joules. Well, no, this isn't the case. This is wrong. Remember that work only counts in the direction that the object is moving. So what we're going to have to do is we're going to have to look at the component of this force that's pushing in the direction that the lawnmower is actually moving. Okay? So what we have to do is we have to break this force vector into its components. And let's say that this is a 50-degree angle. That's 50 degrees right here. So that also means that this is 50 right here. So let's redraw our triangle here just to make it clear. This is going to be force in the y direction, and this is going to be force in the x direction. We have an angle of 50 degrees. So we need to find the component of the force that's acting in the direction that the lawnmower is moving. The lawnmower is moving this way. So we need to find this component right here. So we have to go back to our SOHCAHTOA. We have to choose the one that we want to use. Looks like we're trying to find the adjacent side from the angle. So we're going to go ahead and use cosine here. So we're going to get cosine of theta is equal to the adjacent side over the hypotenuse. Well, in this case, adjacent side is the fx, and the hypotenuse is our 10 newtons here. So let's re-plug these in. So we get cosine theta is equal to the force in the x direction over our hypotenuse of 10. And we want to find f of x. So let's solve for this. So we get f of x is equal to, multiply both sides by 10. We get 10 cosine of 50 degrees. Now 10 cosine of 50, if we plug that in, that's about 6.4. So only out of the 10 newtons that we're pushing on the lawnmower, we're only getting 6.4 newtons actually pushing the lawnmower forward. So to find the work, we can multiply this by 10. So 6.4 newtons times 10 meters, and that is equal to 64 newton meters, or a newton meter is actually the same thing as a joule. So 64 joules is how much work we're actually doing on the lawnmower. We're still pushing with a force of 10 newtons, so we're still pushing with all of that force, but just a fraction of it is actually being used to push the lawnmower forward. So I think we'll end our talk there today. So just to review, we first talked about the variables that we have been using and how we got to F is equal to ma. We multiplied F is equal to ma by distance, and we came out with a formula for potential energy. Remember, just replacing the acceleration with gravity and the distance with height. We also came back to one of our kinematic equations and plugged that into our F equal ma equation, and we derived an equation for the kinetic energy as well. And finally, we ended with work, and we learned that work only counts in the direction that the object is moving. So in this case, even though we're applying a force down of 10, or diagonally down, at a force of 10 newtons, only the component of that force counts for adding energy to the system or doing work on the system. Okay? And finally, remember that our formal definition for work is that we're giving a system energy. When we do work on the system, we give a system energy.